Okay, so far we've considered various methods trying to design IIR filters, right? Um, the method we have considered mainly was the pole zero placement method, which you did previously, where you were able to design the notch filter as well as the bandpass filter, right? But it doesn't end here. There is one way of designing where we are trying to just move from the analog domain to the frequency domain quickly. And the whole idea is that if we try to kind of uh, skew the whole analog filter into the digital domain, then we don't need to necessarily be placing poles and zeros. We just have a nice equation and we are done. Okay, so in this method, um, if you carefully remember, I realize that the whole design of a filter in the analog domain, we are usually dealing with something called S, right? So we have poles and zeros, transfer functions in terms of S. Okay, now in the digital domain, we come to another transform variable called Z. Okay, now S is actually a kind of a planar conceptualization of the poles of a filter and the zeros as well, right? The general thing is that we usually wish that the poles will lie on the shaded portion of the graph, okay? And that's because when the poles are on the left side, they tend to decay and you get a stable filter. Remember, this is an infinite impulse response filter. If you don't get decaying poles, you might be very unstable. But um, this same S plane when it's for the analog domain, but when you conceptualize it in the digital domain, you have to skew all this left region, right? All this left plane into this unit circle, okay, in the digital domain, right? And that's the whole process of the bilinear filter design. It's just skewing from the S domain, where we have this planar kind of concept, to the Z domain, where we have this circular kind of concept. And by a lot of proofs, right, you can deduce that your S can be given by this expression, right? So anytime you have an analog filter, right, the S can be summarized as this expression: K multiplying Z minus 1 all over Z plus 1. However, um, in reality, you don't usually just do this, okay? You don't just substitute S for K, S for K multiplying Z minus 1 over Z plus 1. There are a few things you have to do, okay? Now, the response you get when you do it directly may be undesirable, okay? So there is a bit of um should I say manipulation before you do the substitution. Now, one thing you do is that you have to convert between the analog frequency and the digital frequency, okay? Remember, we are transforming from this S domain to this Z domain. And also remember that the transform is not linear, right? But for most parts, it can be conceptualized as it's linear, okay? But to be able to always get the right values, then we have to do something we call prewarping, okay? And in the prewarping, realize that the analog omega, or the analog frequency, is related to the digital frequency by this whole equation, okay? And now some books try to use k is equal to 1, others try to use 2 over t, right? But no matter which value you use, you should end up with the same answer, okay? So the whole pre-warping is that we are in the analog domain. Now coming to the digital domain, you realize that the weight of the various bands in the analog domain doesn't correspond to the same as the digital domain, right? So we have to pre-warp the filter first to be able to get the corresponding frequency, right, in the digital domain. And we would see an example of that, but just remember when we are doing that step that there is a point where we have to do something we call pre-warping, right? And it's very necessary for our filter design procedure. So let's summarize the procedure. The whole procedure is simple, right? You are supposed to use digital filter specification to determine the normalized transfer function. Okay, so what you are telling me is that they would give you a filter, say a band pass, a low pass filter. Now you have to first find it in a suitable normalized function. Then you have to determine the cutoff frequency. You obtain the analog filter cutoff frequency as well. That is, you do prewarping. Now you denormalize with the prewarp frequency and you apply the Z transform. Okay, it's a lot of talk, but let's try to solve an example so that you don't get bored with the details. So for example, we have here this question. It says determine using the bilinear Z transform method the transfer function of the difference equation for the digital equivalent of the resistance capacitor filter, right? So you have an RC network. Assuming the sampling frequency is of 30 hertz. Now, remember that usually the transfer function of things like this is 1 over what? SRC plus 1 when you draw this analog circuits, right? But I mean, we'll not be going into this. Usually, there are few variations of this, so it's okay memorizing it of it. Now, when it's normalized, it's usually that you make it in the simplest form, or preferably make the coefficient of x 1. Okay. Now, you realize that we are given the sampling frequency of what 150 hertz and a cutoff frequency of 30 hertz, right? Now, you realize that you first have to find it in the digital domain, right? Some normal circumstances, it will just be 2 pi times the 30 hertz, right, to give you the omega p or the analog frequency. However, you have to first prewarp it, right? Because this is without prewarping, right? The frequency you'll be using, right? But you have to first prewarp it. Now, in prewarping, you have to use the prewarp formula, right? And the prewarp formula, I think it's shown here. Okay, it is what tan of omega p multiplying t over 2. Now, remember, you were given t as what 150 hertz. So you're given sampling frequency as 150 hertz. So t will be equal to what the 1 over 1 sampling frequency, and that's what you see. Now, when substitute into this formula, right, you get tan of pi over what 5, which is this. Now, a lot of people make a mistake here when you are doing this calculation, right? For the most part, make sure calculator is in radians. Okay, so I don't know. Probably let me show the error which usually arises. So since I'm still in degrees, right? I'll have to be evaluating. Let me see. It's supposed to be tan of and it's supposed to be omega p. Omega p is 2 pi times 30. Okay, so 2 pi times 30, and t is 1 over 150. Okay, so then all over 2, so it just be times 2 at the denominator. Now when I punch this into the calculator, you realize I get what 0.01, right? And that is wrong. The wrong answer is supposed to be around 0.7265. That's of the simple error that I'm in degrees, not in radians. Okay, so you have to change your mode towards radians, right? And do the calculation again and realize that you are getting it. Okay, yes, so that's one thing you should take a note of. Now, once you do that, then the next part is simple. You are just supposed to follow. So you have been able to find the analog prewarping factor. So you have to put it back into the equation, right? What do? Anywhere you see S, replace it by S over 0.7625. So our original equation was this, right? So the numerator 1 1. The denominator is s, so we replace it with what? S over 0.7625, and that's it. Now, when we simplify all of that, we get this expression. I know that one is easy. Now, once we are done, what we are supposed to do is you are supposed to replace s by the expression what? Z minus 1 over z plus 1. Okay, and that's what we are doing. So, in this equation, the one you see here, when you place s by z minus 1 over z plus 1, it will result in this, right? Then you can go ahead and expand. Okay, now I think I should probably do the expansion together, right? Oh no, yes, I should do it together so that we are able to uh, follow along. So at the numerator we have 0.7625 multiplying 1 plus z, and at the denominator we have this. Now this expression can be simplified as is 0.7625 multiplying 1 plus z over the denominator. We can get 0.7625z plus, okay, no, it's supposed to be 1.7625z minus 0.1548. Okay, now our quest is to get some kind of 1 in the denominator. Okay, so what we actually do is that we divide the denominator by 1.7625z, right? So I think when you divide here by 1.7625z, here by the same factor, and the numerator by the same factor, you end up with this expression. Okay, because we want to get 1 and other expression. Remember that in our original equation, or in our original statement of the transfer function, is some numerator of zeros and a denominator of 1 minus the poles. I'm referring to this equation where you have some summation of zeros, the coefficient of zeros, over 1 plus some expression multiplying some coefficient of poles. Okay, yes. And now when you have an expression like this, you know that you have to expand it such that the zeros are here and you negate what? All the coefficient of the poles, right? Because of this negative you see here. Okay, so that's what you do with your final expression. So on arriving at this final expression, you have a numerator, right? And the numerator will be your x of n's, the denominator will be your y of n's. So you had minus 0.1584 z minus 1 at the denominator. You know that to be a y of n, right? And to be y of n minus 1 because the power of z is minus 1. Okay, so positive 0 point that, because I said you negate the denominator coefficient, and the numerator it was 0.4028 multiplying 1 plus 0 is the power minus 1. So it means that 0.4208 is a factor outside. Multiplying 1 is the same as 0 is the power 0, right? So it means that n plus 0. Okay, so that's what it is. So x of n. X of n, because it's at the numerator, plus 0.4208 multiplying z of minus 1. Okay, so x of n minus 1. Yes, and with that, you have successfully designed the filter using the bilinear Z transform. And that practically solves this question. And a very similar one is this, right? Where you are actually given the required analog transfer function as this whole complicated expression, and you are asked to solve. So it's actually the same procedure, right? You are given parameters that your cutoff frequency should be 150 hertz and your sampling frequency should be what, 1.28 kilohertz. So your critical frequency, or for the digital filter, also just 2 pi times 150. Now you can find the pre-warp frequency of the filter, which By now you should know it's this formula, and entering it rightly into your calculator, you should get 0.3875. Then you come back to substitute every s you see by what? S over 0.3875. So you realize that it was what? X squared plus root 2 multiplying s plus 1. So you have s over omega p prime squared plus root 2 multiplying s over omega p plus 1. Then you expand. Okay, so this whole process is expansion, and this is just algebra. So you don't really need to stress. I don't need to stress myself explaining. Then the next step is that anywhere you see s, replace it by what? Z minus 1 over z plus 1. Yes, and now when you do that, you arrive at this expression. Okay, yes, and that's it. You have you now have this expression, but this expression is not enough. You have to have 1 somewhere in the denominator. So what they did is they have to divide through by what? Z squared, and dividing through by z squared will leave you with 1 here. Then here will become z minus 1. Here will become what? 0.356 z minus 2. Then the numerator is as you see, right? Remember, you have to divide the numerator by z squared as well, right? Since you divided the denominator by z squared. Now, doing that would give you the final equation where you have to express it. Remember, it's the same procedure, right? So here they didn't write the answer, but let's try writing the answer out. So let's write the y of, so the answer will be y of n being equal to, this is a negative figure, so it will become positive, so 1.0048 times y of n minus 1 minus 0.3561 multiplying y of n minus 2. Then now let's do the x of n plus the x of n are all multiplied by the expression 0.0878, right? Now here is 1, so that's the same as what? X of n minus, now when it's x of n, when you see minus it's minus, when you see plus it's plus, minus 2 x of n minus 1 plus x of n minus 2. Yes, and as long as you have it, that's your filter equation for this question as well. So yeah, thank you very much for your time. See you on your next video.